Hi, welcome back. In this video, we are continuing to talk about sampling distributions. The last example, we looked at a sampling distribution of sample proportions, and this example is going to look at a sampling distribution of sample means. All 423 Wisconsin public schools were given a rating by the Wisconsin Department of Public Instruction based on several variables. The mean rating reported was 71.5 and a standard deviation of 4.87. To do a follow-up study, a random sample of 40 schools was selected. In this sample, the mean rating was 70.9. One of the researchers is alarmed, thinking the report may have been mistaken. Do you think this sample result is unusually low? Explain. So to start, I can tell that this is a sampling distribution question because the question is asking what's happening with a sample. So then I'm trying to decide if it's proportions or means. In this case, I'm given a truth for the mean and standard deviation, and I'm given a mean for a sample. So this is measured data, whereas the previous question was counted data. So this is going to be a sampling distribution of sample means. So I first want to start out by defining mu. So I'm going to define mu, or I'm going to define it as mu sub x, is the true mean rating of all Wisconsin public schools. So I am defining my parameter here. I could also define x, in which case x would be the rating of a single Wisconsin public school. And this mu is the true mean. Because my population is 423, and these are the values, the mean and the standard deviation based on that population, I know that my true mean rating, my true mu sub x, is equal to 71.5. And my true standard deviation is equal to 4.87. Now I am looking, if this is my true mean and this is my individual, my question here is going to be asking about sample means, x bars. So I'm also going to define x bar here. X bar is the mean rating of a sample of Wisconsin public schools. And in this case, I'm looking at a sample of 40. So we are wanting to describe, what do I expect to happen from this population if I take samples of 40 schools and I look at their mean? Well, the good news here is that the central limit theorem really is helpful with this. The central limit theorem says that the distribution of sample means is approximately normal, with a mean of the sampling distribution that is equal to the mean of the individual, and a standard deviation of the means that is equal to the standard deviation of the individual divided by the square root of the sample size. The distribution is approximately normal if either of these conditions is met. The first is that I can know that my original population is approximately normal, or I need n to be sufficiently large. What we find is sufficiently large if nothing is known about the original population, or if the original population has incredible skew, multimodality, things that are really wonky. A sample size of 30 is large enough that the distribution of sample means from that population will be approximately normal. So if nothing is known, we want n to be about 30 or larger. If our original distribution, we know it's got some slight skew or it's fairly normal, we could have a sample size that is much smaller than 30, like say 15, that would make this be true. So what we need to do now is we need to go through our check-ass for the central limit theorem. These are the same three broad assumptions that we checked when we did the sampling distribution of sample proportions. They just have a slight change. So, the independent criteria. Well, I am going to assume it's reasonable, but I'm sampling without replacement, which again, we are violating the independence. So because I'm violating independence by having no replacement, I need to check my sample size. My sample size is 40. That is less than 10% of 423. This is really close. 40 is less than 0.1 times 423, which is 42.3. We are very close to not meeting this criteria, but we do. So we may assume and proceed with the independent criteria. The next thing we want to check is our sample size. And when we are checking our sample size, we want to be thinking about when we were looking at the sampling distribution of sample proportions, that sample size check, the NP-NQ, was really the check that let us use the normal model. That NP-NQ being greater than or equal to 10 is what allows us to use the normal approximation for the binomial model, which is how we use this. Here, our normal check comes from, or our sample size check comes from the central limit theorem. In this case, my original population is unknown. So the original population distribution is unknown. They have not told me if these scores were normally distributed or not. They haven't told me if they had skew or if they were bimodal or anything like that. So because I know nothing about the original population, I need to check the sample size. And we said that n is 30 is traditionally large enough. So n equals 40 is greater than 30. So my sample size is large enough for the central limit theorem. And we want to call out that this is related to the central limit theorem. That this sample size check is the central limit theorem check. It's really important that we include that. Now, random. Let's go back up to my problem statement here. And they say that we took a random sample. So random sample is stated. This means that the distribution of sample means is approximately normal. And this sample size check is the main check that's letting me use that. Okay, so now that I know the distribution is approximately normal, I want to find the mean of this distribution and the standard deviation of this distribution. And from the central limit theorem, I know that the mean of the distribution of x bars is equal to the original population mean. So I expect the distribution of sample means to be centered about 71.5. And I expect the standard deviation, or the spread, to be smaller than the standard deviation of the original distribution. There will be less variability in my standard deviations than there was in the original population. So if I take 4.87 and I divide it by the square root of 40, I get 0.77. So here I have my distribution of the sampling distribution of sample means. In this question, that's not what I'm being asked. I'm being asked, do I think this sample was unusually low? So I have been told that I have a sample that was found to be 70.9 with a sample size of 40. So this is my sample information, and they're asking, is this really low if this is the distribution I expect? So I am going to draw the model. X bar is approximately normal with a mean of 71.5 and a standard deviation of 0.77. So this observation, this sample we got is 70.9. And the question we're being asked, is this unusual? Is there something about these 40 schools that's making me question this? So I want to find this probability, the probability that a sample mean is less than 70.9. I have the distribution, the model of sample means, so I'm going to use my calculator. I'm going to do normal CDF. My lower limit is negative infinity. My upper limit is 70.9. My mean is 71.5, and my standard deviation is 0.77. And that tells me that this area is 0.2179. The probability of a sample of 40 Wisconsin public schools having an average rating of 70.9 or less is about 21.79%. This is not unusual. And we can think of 21% as not unusual because this seems like, well, then I would expect something like this to occur about 1 in 5 times. 20% would be 1 in 5 times. So this outcome, about 20% or about 22%, so about 1 in 5, will from this distribution will be 70.9 or lower. So this is not an unusual result, and there's no real concern here.